as you can see here, I've covered 2 exercises with 1 explanation. So in 12D, we're going to look at the integration, and note that it's not saying integration of logs, because that actually doesn't exist. You can see here the red line through integration log of x. We can't do that. So what we will be doing is the integral of 1 on x, and 1 on x is called the reciprocal function. So we will be looking at integrating the reciprocal function. When we've learnt the theory of that, then we do the applications of integration. And they're no different to applications of integration that you've seen before. So area under a curve, volume around the x or the y axis, those sorts of questions. So the applications are just the same, just like the applications of the derivative. Finding the tangent, the equation of the tangents, etc. was no different, just because the function is a log, to what it was with the other functions. The integral is similar, that the applications of integration are the same as what you've previously seen. Okay, so you might remember, or if I just flip back to before that, back to here, if we actually have a look at some of the answers to differentiating. So differentiating A on B, we're differentiating the log of x on 7, differentiating the log, then you end up with this 1 on x. Let's find another example. Differentiating the log of 7x, you still end up with a 1 on x or 1 on x. Any others? That was a more difficult one. The log to base 10 is a constant times 1 on x. So, yep, there's a lot of times when you differentiate that you actually get 1 on x. So it stands to reason that if you integrate 1 on x, it would take you back to the log function. So that's basically what you need to be able to recognise. There's no sign of log here, no sign, but you just have to know that where the integral of 1 on x is actually log, the log function. Up until now, it's been avoided. You've done other fractions, but not this exact fraction, because the only rule you previously had was to add 1 to the index, divide by the new index. That would be giving you an index of 0, and dividing by 0 creates an error. So you can't integrate this 1 on x using the previous rule. However, we do know with the graph of 1 on x looks like this. Is there such a thing as area under that curve? And yes, definitely there is area under the curve, which consequently means we should be able to integrate it. So we can integrate it, and the integral is actually the log function. Remember, integration reverses differentiation. So if we've got straight out the integral of 1 on x with respect to x, it'll be log of x plus a constant. Easy, straightforward, must be learned. What about when we start to complicate it a bit? We've got the integral of 1 over some like 2x plus 4, or 3x minus 7. This time, we know it's going to be the log involved, the log of ax plus b, because that's how it came into the denominator. But when that was being differentiated, it would have been multiplied by a. No sign of being multiplied by a here. So where did the a go? There must have been a 1 on a. So if you can actually see that you've got the integral of the derivative of a function, then because that function is in the denominator, you know it's come from differentiating the log of that function, and then of course you've had to multiply, which will place into the numerator, the derivative of your function, and don't forget your plus c when you're integrating. So what do you see here with this first example? Hopefully you see into the denominator is an expression with x in it. You've also got x in the numerator. We never take the integral of a fraction looking like that unless we can simplify it, and we can't simplify it, and we're not going to bring this x squared plus 2, put it in a bracket and bring it up to the top, because we still would have difficulty integrating that. So we have to look a little more carefully and closely. We can actually see that this 2x is the actual derivative of x squared plus 2. So it's a very good example of this rule here, where we're integrating, where we've got the derivative of this function on top and the function in the denominator. So we write that as the log of x squared plus 2, and of course always plus a comma. Oh, no, it's not. That looks better. It's a definite integral. If it had been an indefinite, no values on your integral sign here, we would have had a plus c. And need to be really careful on these log integrals, because we rarely get a 0 substituting x equal to 0. So so you've always will need to substitute x as 0 in. And also, just before we start actually evaluating our log or our integral, just check. You need to do a little check of the derivative of the denominator is actually what's sitting in the numerator. You'll see in the next example that we actually have a bit of a problem because it didn't work out this way. This was actually a nice question because the numerator was the derivative of the denominator. Back to here, subbing in our values, you get log 3 minus log 2, using your log rules. Log 3 minus log 2 is log of 3 on 2. Look, let's have a look at this next one. So it's another definite integral from 0 to 2 of x on 9 minus x squared. So again, you know, we've got a fraction, integrating a fraction. And unless we could simplify it, then it becomes a log function. However, if we do d dx of the denominator, 9 minus x squared, you get minus 2x. Now that is not what has been placed up here. So what I would say is set up your integral. Introduce something more into it. The only number we can introduce into it is 1. And you will see then we have a correction term. Now what I mean by that is, so we want the integral from 0 to 2, and I'm going to make this minus 2x over 9 minus x squared dx, but I've introduced minus 2 into the numerator. I'll have to introduce a minus 2 into the denominator. The only number that I can really introduce here into my integral is the number 1. And so I'm choosing 1 in the format -2 on -2. So integrating that, I'm going to take this, this is really 1 over -2, I'm going to take that out of the integral. It's like a constant sitting in there. I'm going to keep all of that, because then this is really nicely log of 9 minus x squared. So you can see I've deliberately set up the integral by using or introducing a variation of the number 1. And what I've actually needed is an additional -2. How do I know that? Because I did a little calculation on the side here showing what the derivative of the denominator actually is. Once I've introduced that, I then need my correction term. So this becomes the correction term, which translates to the number -1/2. I've put an additional constant in there. I'm going to take it out and then proceed with integrating. So this would be the log of 9 minus x squared, very nicely, and I want that from 0 to 2. And so you can see there that I've subbed in x is equal to 2, and like I was saying in the previous example, you will need to sub your 0 in, because this won't all just disappear to nothing. And you get log of 9, simplifying, we've got log 5 minus log 9, using new log rules, -1/2 times the log of 5 on 9. Hopefully you will then be right to work your way through exercise 12D and 12E. Get lots of practice at integrating, looking at fractions, altering them if you need be, putting some variation of 1 in, and introducing a correction term.